This is the third behavioral design pattern, and this one is called interpreter pattern. It is a pattern you use when you are working on a problem that can be expressed in a domain-specific language. The pattern provides an interpreter for that language. I'll start with a quick summary of what we are trying to accomplish with this pattern. The interpreter pattern is a good choice when you are trying to accomplish the following. You have multiple objectives that exist in a well-defined and well-understood domain. The objectives can be expressed with a simple language. Okay, let's go through these points. This pattern is of great help when we are working with so-called domain-specific languages, or DSLs. A domain-specific language is a simple language with its own grammar that describes a solution in a specific domain. A good example is SQL, or Structured Query Language. This is a custom language for retrieving and modifying data within the domain of a relational database. The language allows you to express complex operations, for example a multi-table join, using a very simple grammar. Databases use an SQL interpreter to validate and execute SQL queries. You can create your own custom language for any domain you want and use this pattern to build an interpreter. The interpreter codifies the language grammar and syntax rules and executes commands written in the language. The interpreter pattern offers a number of benefits. First of all, the domain-specific language provides a very compact representation for queries, commands, or business rules in the given domain. Complex operations that might require lots of executable code can be represented with very simple keywords or grammar rules. The pattern also introduces flexibility. The interpreter hides the complexity of the domain from the rest of the application architecture. If the domain changes for any reason, all you need to do is write a new interpreter to make your existing code work with the new domain. The interpreter pattern also has a disadvantage. The interpreter masks the complexity of the problem domain from the rest of the application architecture. Clients only need to express queries, commands, or rules in a high-level language, and they are completely shielded from the complexity of executing this language. So there is a risk that you are writing what appears to be an elegant and compact language expression, but that the low-level implementation of that expression is overly complex and does not perform well. Performance bottlenecks in domain-specific languages can be very hard to track down. Here is the UML diagram of the interpreter pattern. The pattern uses a minimum of 5 classes. At the center of the diagram are 3 expression classes. The term expression in this pattern refers to a rule, keyword, operation, or literal in the domain-specific language. There are 2 kinds of expressions. A terminal expression is an expression that does not refer to any other expression. For example, in mathematical expressions, a number is a terminal expression. It's an independent symbol that does not relate to or operate on other parts of the expression. The other kind of expression is a non-terminal expression. This is an expression that refers to one or more sub-expressions in the language. A good example is the mathematical plus symbol. It adds two sub-expressions together, the one on the left of the plus symbol and the one on the right. To build a basic mathematical expression interpreter, all you need to do is create one terminal expression class for a numerical constant and four non-terminal expression classes for the plus, minus, multiply and division operators. Okay, back to the classes. The abstract expression acts as the base class for all other expression classes in the language. You can see that there are two classes derived from abstract expression. They are terminal expression and non-terminal expression. These correspond to the two types of expressions we just discussed. Each expression class has an interpret method that executes the expression. The method receives a context, which contains the global state of the interpreter. Each expression performs a specific operation and optionally reads and updates the global state to reflect that operation. Finally, we have the client class. It holds a reference to the language context and initializes an expression tree, which is a hierarchy of terminal and non-terminal expressions that define the syntax and grammar of the domain-specific language. To execute a language command, all the client needs to do is initialize the context and provide it in a call to the interpret method of the topmost expression in the expression tree. That expression class will then call the interpret method of other expressions to process the language command. Sometimes you see one extra class in the pattern called a parser. This is a special purpose class that parses the language and builds an expression tree from it. I will show you a simple parser in my example. So let me clarify the pattern a little further by showing you a concrete example. I am going to build an interpreter for processing mathematical expressions. To make it easy on myself, I am going to process reverse Polish notation. This is a mathematical language where all numbers get pushed on a stack, and all mathematical operators process values on that stack. For example, take the expression 5 plus 42 minus 10. So we know the answer is 37. In reverse Polish notation, the expression looks like this: 5, 42, 10, minus, plus. So here's how that works. First, the number 5 gets pushed on the stack. Then the number 42, and then the number 10. Next is the minus operator, which simply takes the two topmost numbers on the stack, subtracts them, and pushes the results back on the stack. So in this case, the operator subtracts 10 from 42 and pushes the number 32 back on the stack. Finally, the plus operator takes the two topmost numbers on the stack, which are now 5 and 32, and adds them together. So the final result is 37. I am going to build a very simple reverse Polish notation interpreter that can interpret expressions with integer numbers and one of the four basic operations: addition, subtraction, multiplication, and division. I will implement the pattern with these classes. Note the extra parser class. I will add it to the solution so that I can interpret a string containing RPN expressions. Okay, let's take a look at the code. I will start with the abstract expression class, which is nothing more than an abstract base class that declares the interpret method. You can see that the method does not expect any arguments, because my interpreter has no global state. The method does return an integer, and this is the numerical result of the expression. And here is the number class, which is derived from abstract expression. You can see that it has a constructor for initializing the class with a specific integer. The interpret method simply returns that integer. Very simple. So let's move on to something more complicated. Here is the add class. It has a constructor that expects two sub-expressions to add together. The interpret method calls the interpret method of the two sub-expressions to get their values, and then simply adds these values together and returns the result. All other non-terminal classes work exactly the same way, but each uses a different operator. Okay, and finally, here is the parser. There's a parse method here that receives a string. This is the text representation of the RPN expression. The parser splits the string on the space character and iterates through each word. Anything that is not a mathematical operator is treated as an integer. The parser parses the integer, creates a number expression, and pushes it on an expression stack. Now look at this code here. If the current word is a plus character, then the parser pops the topmost two expressions of the expression stack, creates a new add expression with these two sub-expressions, and pushes the add expression back on the stack. So, this code actively builds an expression tree by parsing the input string and producing an expression tree in memory. To execute the expression, all I need to do is call interpret on the topmost expression on the stack and capture the return value. Okay, let me run the program to prove that everything is working fine. I'm compiling the code now. And now I'm running the program. Okay, the program is now asking me for an RPN expression. I will type the same one I used before, so 5, 42, 10, minus, plus. And there you go, the answer is 37. Everything works. Here is a quick checklist you can use to implement the interpreter pattern. First, decide if a domain-specific language offers a justifiable return on investment. Then define the grammar for the language. Map each grammar rule to an expression class. Organize the expression classes into a hierarchy, similar to the composite pattern. Decide if you need a global interpreter state, and if so, put it in the context class. Optionally, add a parser to build an expression tree from a language string. And finally, have the client use either the parser or a pre-built expression tree to execute language commands. And here are some final comments. If you are still wrapping your head around the code example I showed you, then here's a diagram that might make things more clear. I typed the following expression on the console: 5, 42, 10, minus, plus. And this is the expression tree that the parser made from it. You can see that the final add operation is at the top of the tree. By calling its interpret method, I can execute the entire expression and get the final result of 37. Each non-terminal expression in the tree recursively calls the interpret method of its sub-expressions to assemble the final result. If the interpreter has a very complex global state, you might consider using the state pattern instead of a simple context object. And for very large expression trees, you can consider using the flyweight pattern to share instances of terminal expressions. Okay, so here is a summary of what we have learned. The interpreter pattern provides an interpreter for a domain-specific language. You can add a parser to build the expression tree from a language string. The pattern provides a very compact representation for queries, commands, or business rules in the given domain. But it also masks the complexity of the problem domain from the rest of the application architecture. You can combine the interpreter pattern with the state or flyweight patterns.